will be as the BGA, British Geotechnical Association, will be I'll be co-chairing this as a joint meeting of our specialist knowledge societies, and yeah, I'm delighted to be here.
Okay, thank you. So there are 14 specialist knowledge societies under the ICE umbrella. So BTS is one of those. I think us and the BGA are probably the two largest. So on to this evening's lecture then. HS2 is a project that's never far from the news, not always for the right reasons. So I'm really delighted that a couple of the people from the client are going to come down and speak to us this evening. So our first speaker is Martyn Noak. He's the head of ground engineering and tunnelling. Martyn started his tunnelling career in 1996 on the Jubilee Line extension at Green Park Station as a shift engineer with Tarmac Construction, where he learned the traditional art of square works and low mechanised shield-driven tunnelling in London clay. Following a stint at W.S. Atkins Rail, where he designed the pedestrian subway access to Gunwharf Quays through the railway arches at Portsmouth Harbour, Martyn joined Halcro as part of the Rail Link Engineering Consortium on the Channel Tunnel Rail Link at Stratford. At RLE, he was the designer of the Barrington Road ventilation shaft, numerous tunnel opening sets, and the vent adits along the London Tunnels route, and was part of the team working on ground movement assessments, including the mitigation works for the undercrossing of the Central Line. Returning to Halcro HQ in 2004, the company was consumed by CH2M and then Jacobs, where Martyn became the head of discipline for tunnels in 2017. He then worked on the DLR extension at Woolwich, the TWAO design for the Northern Line extension to Battersea, the tender design for Stonehenge, twice, 2005 and 2020. Well done. And was the designer's project manager for the upgrade of the Airlywell station at Tottenham Court Road station upgrade from 2012 to 2020. Martyn joined HS2 as head of tunnel engineering in 2021 and became head of ground engineering in 2024. Okay.
And also speaking tonight, we have Mark Lemmon, who is the lead tunnel engineer for HS2. Mark is a member of the Institute of Civil Engineers, but he started out as a geologist working offshore at CEng Engineering. Then in 1999, he probably made the best decision of his life by going and doing soil mechanics at Imperial College. Following this, he spent a year at Stent Foundation as a design engineer. Mark joined Halcro, where he worked on numerous geotechnical engineering projects. Since 2006, Mark has been involved in a series of the UK's major infrastructure projects, including Crossrail, Thames Tideway, and HS2. Mark's involvement on HS2 was initially as a project manager during the ground investigation and early contractor involvement phases. Then again in 2022, Mark returned to a technical role and in his current position as lead tunnel engineer for HS2, where he specialises in the fields of instrumentation and monitoring, asset protection, ground movement, and the geology. Mark hopes to leave a legacy for the vast HS2 ground movement dataset, and his initiative for a national tunnelling data hub, which he is currently working on with a team at City St George University.
Okay, thank you, James. So, first speaker, please.
Okay, good evening, everybody. Thank you, John, for the introduction. Myself and Mark work for the core engineering team at HS2, and we cover tunnelling for the whole of the 225-kilometre route from Euston to Birmingham. And whilst we are representing HS2 tonight, we're going to present on some of the fantastic work that all of the tunnelling joint ventures have been undertaking for the past 5 years. In this talk tonight, I'll provide an update of progress on the tunnelling to date. Mark will discuss the geological setting and some of the challenges that this brings. And I will close off with some of the tunnelling statistics and a look at the future tunnelling that is yet to be started. Okay, so a few words on our organisation. There's 5 of us in the core team, and we are separate too, but work closely with the integrated project teams that many of you here, I'm sure, are members of. And those are made up of tunnelling, of an integrated team of client, tunnelling contractor and designer. So we have 44 kilometres of twin bore tunnel and 8 kilometres of cut and cover or green tunnel, comprising some 19% of the route between Euston and Birmingham. So I'll split this geographically and into the contracts, and you can see how we have starting off with the London tunnels, constructed by SCS. We have the Euston Cavern and Euston crossover tunnels, the Euston tunnels, the Old Oak Common tunnels, Norfolk tunnels east, Norfolk tunnels west, Copthall tunnel, and 6 intervention and ventilation shafts. And you can see all the details I provided on the table there. Next up the route, we've got the Chiltern tunnels with 4 intervention and ventilation shafts and 1 intervention shaft only. And then we have the EKFB green tunnels, the Great Worth green tunnel, Tipping Warden green tunnel, Wendover green tunnel, and then further up north, up into Warwickshire, we have the Burton green tunnel, Long Eatonton Wood green tunnel, Long Eatonton Wood bore tunnel, and the Bromford tunnel constructed by BVV. And there's 1 intermediate shaft and ventilation shaft constructed in that contract. So I'm going to spend the next few minutes describing each of these in turn and the current progress. And just to say that there's simply too many assets to go into great detail on each. The purpose of this presentation is to provide this part of the presentation is to provide a project update. So if I've missed out or glossed over any particular aspect anyone in this room is involved with, then I do apologise at the outset. I'd also like to say I won't be going into particular detail or describe necessarily some of the challenges that the contractors have met, because that's something for them to describe in future meetings to us. Following on from that, I do have a few words to say on aerodynamic considerations and how the magnitude of tunnelling has increased during the route development, as I think that will be of interest to many of us here. So before I do that, I'd just like to quickly show you the typical tunnel cross sections that we've been building. So we have 4 tunnels between 7.55 and 9.1 metres ID. The slide says 7.44, that's a typo, I'm afraid, 7.55. We have 87 spray concrete line cross passages between 12 and 30 metres in length and around 3.5 metres in internal diameter. And we have some large diameter SCL tunnels up to 11.25 metres across the internal diameter of the axis. And we have the double cell precast tunnels with each cell approximately 8.5 by 8.5 metres wide. So our journey starts from east to west, starting with the London tunnels constructed by joint venture SCS. These are predominantly bored and mine tunnels with a short section of cut and cover tunnel at the western end. I'm leaving out the Euston tunnels for now. I'll come on to those later as they've not yet been launched. So, starting at Old Oak Common Station, which is just there, which will be the temporary terminus when HS2 opens. At the eastern end of this 1 kilometre long station box, we have the Euston stub tunnels. Which of these ones just here? And so these are SCL tunnels from which the Euston tunnels will be launched, and they're 80 metres long approximately for the upline and 135 metres long for the downline. These have all been completed and the TBMs are sitting within and they're about 95% assembled. It's worth noting here a key constraint of sharing access with the station box contractor for the installation of the TBMs, which there'll be more on that later. And then access for construction of the stubs themselves was through the Atlas Road Logistics Tunnel. And that is an 850 metre long, 6.2 metre diameter EPB tunnel, completed in November 2023 using a second-hand Crossrail machine. This tunnel connects the logistics hub at the Western Euro Terminal with the very very eastern end of the Old Oak Common Station, and will be key to delivery of the Euston tunnels. We shall hear about that later. At the western end of the station, we have the Old Oak Common Tunnels East. It's a bit confusing. So these connect the Victoria Road crossover box, which is a large crossover box to allow for switches and crossings as train switching over from one line to the other as they go into the station. So these have been driven. So just show you, sorry. So those are the Old Oak Common Tunnels West, Victoria Road crossover box. So these were driven from the Victoria Road crossover box towards Old Oak Common Station. They're 370 metres long and our typical running tunnel diameter about 7.5 metres. They fan out, although they do fan out either end to about 13 metres to allow for the tracks to diverge for the switches and crossovers. So completion of these, the primary lining is 75% complete, and we're just about to start. We've just started doing secondary lining. The primary lining is now on hold because we're waiting for some utility diversion to be completed at the west end of the Old Oak Common Station box before we can complete the drive. And that will be starting again probably next summer. In terms of thicknesses and so on, the primary lining is 300 to 400 millimetres thick, and the secondary lining sort of 275 to 400. At the western end of the Victoria Road crossover box, we have the launch site for the Norfolk Tunnels East via short SCL tunnels and the Victoria Road ancillary shaft. So moving on to the Norfolk Tunnels East. So these were launched from the Victoria Road crossover box and Victoria Road ancillary shaft in February and March 2024, and they travel northwest for 5.6 kilometres to the reception shaft at Green Park Way, up that way via an intermediate shaft at Westgate. So as you may have seen in the press, both machines have successfully completed their drive in the summer of this year, and the tunnels are 8.1 metres ID and were driven by an EPBM machine in semi-open mode for the majority of the drive. There are 14 cross passages up to 30 metres in length, comprising a primary lining of about 250 mm thick, a sheet waterproofing membrane, and a cast in situ lining, secondary lining of 250. Mark will cover the ground conditions in more detail shortly, but suffice to say that with the exception of the last cross passage, no ground treatment was required for their construction. Westgate shaft is one of 12 on the route, providing ventilation and emergency services access. So due to surface constraints on the SCS contract, there's no single common shaft design necessarily. This particular one is a single shaft with ventilation adits branching off, as you can see in the 3D model at the top, and then the photograph immediately underneath it of the completed adits. The Green Park Way shaft is the reception shaft for both the NCE tunnels, which are driven from east to west, and the NTW tunnels, which are driven from west to east. And I'll leave it to SCS to describe their reception can design and the big lifts used to receive all the machines, which have all been successfully received now. Okay, so the Norfolk Tunnels West, so they, as I said, they were driven from west to east, and they were driven from a portal structure 250 metres long at West Ruislip in West London. Shallow launch methodology was used in this instance. I believe that's due to alignment considerations. And in order to facilitate that, we installed some temporary kentage at the portal. Okay, so the tunnel is 8.8 metres in diameter, was driven by an EPBM in closed mode, 7.8 kilometres to Green Park Way shaft, via intermediate shafts at South Ruislip and Mandeville Road. There are 20 cross passages, similar construction to Norfolk Tunnels East, and due to ground conditions, a mixture of dewatering and ground freezing was employed. So the Norfolk Tunnel West drives broke through into Green Park Way shaft in December 24 and April 2025. So the final section of tunnelling for SCS is the Cockthorpe Tunnel. This is a cut and cover tunnel approximately 1 kilometre west of the Norfolk Tunnel portal. It's a twin track, bi-directional, cast in situ cut and cover tunnel with a maximum overburden of about 16 metres. Originally, this was intended to be a cutting, but the tunnel was introduced partly to assist with the reuse of spoil from Norfolk Tunnels West. It's the only twin track tunnel on the project, and consequently has a number of permanently open air shafts for ventilation and aerodynamic considerations, You can see clearly in the photo the two track alignments with the robust curve in between for derailment. The west end of the tunnel, it connects to the Colne Valley Viaduct, which I'm sure even most of us tunnel engineers have heard of, and probably secretly impressed about. This can be seen in the bottom left-hand image. So now we move on to the Chiltern tunnels constructed by a line. So I guess everyone in this room is probably familiar with the Chiltern tunnels, the longest rail tunnels in the UK, 16 kilometres in length and 9.1 metres internal diameter. These were driven by a variable density slurry machine at a depth of up to 90 metres through chalk, with the added pressure of the undercrossing of the M25 within 300 metres of the launch. The tunnel passes through 5 shafts at Chalfont St Peter, Chalfont St Giles, Amersham and Little Middleton and Chesham Road, and these are up to 63 metres deep from ground level to rail level. So these shafts are typically a single design comprising a circular diaphragm wall shaft with connection adits. Head houses are designed to look like agricultural buildings and successfully blend into the surrounding countryside, as you can see from the photograph in the middle there. There are 37 cross passages in the Chiltern tunnels. Construction process is the same as for the Norfolk Tunnels East and Norfolk Tunnels West. All the cross passages were grouted prior to excavation, with some requiring a significant grouting campaign due to the 2-bar water pressure. Breakthrough at the North Portal was achieved in March 2024, within 3 weeks of the original programme, which I'm sure you'll agree is a pretty phenomenal achievement given the length of tunnelling that's been carried out. The tunnel is complete, has been handed over to HS2, and the shafts are not far behind. So whilst we're on this slide, it's take a look at the bottom right-hand image, and you can see the launch portal. And I'll just show you can just make out the trace of the M25. Just there, which really shows how close it was to the start of the drive, and you can imagine how concerned everybody was that it was going to go smoothly. So EKFB are building the green tunnels at Wendover, Chipping Warden and Greatworth. So in terms of length, the Wendover green tunnel is 1.4 kilometres, Greatworth is 2.1, Chipping Warden is 2.5. Predominantly for environmental reasons, these 3 tunnels are constructed using the same Matier arch methodology. Used extensively on the continent, I understand. This is the first time this method has been used in the UK, and it's believed the first time for such a long length of tunnel. The structure consists, excuse me, the structure consists of a 5-piece arch, 2 outer walls, a central wall, and two arch roof pieces, with a cast-in-place invert tied to the walls with double hoop bars. The maximum overburden is about 10 metres, and for Chipping Warden Green Tunnel and Greatworth Green Tunnel, you've got permanent road diversions over the top. A dedicated factory was established at the Stanton Precast factory in Derbyshire for the casting of all 10,000 elements required for these tunnels, and production is around 90% complete at the moment. Following precast installation, sheet waterproof membrane is rolled out over the top and welded to another one that's been placed underneath the blinding, and then backfill commences in carefully controlled layers. A quick word here on continuous improvement. Over the course of 2025, the contractor has come up with over 15 initiatives to improve productivity, such as prefab reinforcement for the invert cages and installation of those by a gantry system. And over the course of these improvements, we've increased productivity by about 200% in the course of the year. So that's a real success story, I think. Okay, moving on to BBV's tunnels. They consist of the Long Ixington Wood Green and Board tunnels, the Burton Green Tunnel, and the Bromford Tunnel. Long Ixington Wood Green Tunnel is an 8.8 metre diameter tunnel, 1.5 kilometres long, under Long Ixington Wood, bored using a variable density slurry machine through mudstone. It's got 3 cross passages, same construction as before, and the first drive commenced in December 21 and completed in June 2022. Whereupon the machine was transported back to the start and launched in 2022 for the second drive, which completed in April 23. And one of my favourite images from the job so far is in this one in the middle, showing the cutter head being driven through the village of Ufton on its way back to the launch portal for the second drive. The TBM was then repurposed as a smaller TBM for the second drive at Bromford, 7.55 metre diameter Bromford tunnel, which I'll talk about in a moment. There's a short 430-metre section of cut and cover tunnel at the south end of the drive, as can be seen in the photos. The Burton Green Tunnel is located in the village of Burton Green, which is about 2 kilometres west of the University of Warwick campus near Coventry. It's 770-metre long tunnel consisting of a 520-metre long in situ diaphragm board and cut cover tunnel with porous portals at either end, and then immediately north of it is a further kilometre of retained cut consisting of a mixture of construction techniques, in situ concrete, diaphragm wall and secant piled. Bromford Tunnel, so our last tunnel on the route, is a 7.55 diameter tunnel bored using a variable density slurry machine up to 35 metres below ground level on the approaches to the terminus station at Birmingham Curzon Street, 5.8 kilometres long. It's got a single intermediate shaft consisting of diaphragm walled circular shaft with sprayed concrete adits, adit connections for ventilation, services and personnel. And one of the key constraints of this tunnel is the Bromford viaduct that carries the M6 motorway above. So this piece of critical infrastructure sits within the 1 millimetre settlement contour for about 700 metres, and both machines have traversed underneath this without any effect whatsoever, which is great news following 5 years of negotiations with National Highways. So this tunnel was launched from east to west, Drive 1 completed in May of this year, and Drive 2 completed on Monday this week. Okay, so our tunnelling journey to Birmingham is complete. I've now got a couple of slides on inverts and walkways, tunnel aerodynamics, and the development of the tunnelling route. So within the scope of our tunnelling contractors is the first stage invert concrete and the walkways, which are shown in pink, blue, and green in the top image up there. So Align and SES elected to pour their invert concrete concurrently with the tunnel construction by using a movable bridge under which a section of the invert, including the carrier drain and the catch pits, was cast. This allowed the servicing of the TBM to be pretty much uninterrupted. You can see a view of the top of the bridge on the top left-hand image, and then you can see a view from underneath it at the bottom where it's been prepared for the next pour. This method had significant programme benefits. As I say, the invert continued as the tunnel was driven without having much of an impact on tunnelling operations itself. BBV have chosen to cast their inverts using a paving machine at the end of the job for Long Eaton to Moorland for Bromford. I believe that that's due to allowances in the programme at Long Eaton to allow that to happen, and spatial constraints at Bromford, which make it much more difficult as it's a smaller diameter tunnel. In terms of the walkways, Align elected to use a slip forming machine to cast the walkways, and once it got going, there was an excellent productivity. An average of 80 linear meters for a 12-hour shift was achieved. Due to other cross passage work, shaft connection work, and general access constraints, SES have instead adopted to use a movable formwork bridge, and you can see an image of that on the right-hand side, and that can move from place to place where the availability is to construct the walkways. Current progress is averaging at about 28 cubic meters a shift. That one. Okay, so moving on from project progress, so very few words on scheme development. I've only been associated with the project for 4 years, and a considerable amount of route development has obviously taken place before that. The project's been going for a long, long time. These next two slides show the extent of the tunnelled route as the project has developed. So I've chosen 2 points in time. So this slide shows the current route with 44 kilometres of bored tunnel and 8 kilometres of cut and cover tunnel, which I've just described. Bored tunnel's been in red, cut and cover tunnels in green. So to spot the difference, this slide shows that back at post-consultation stage, i.e. in 2022, before the hybrid bill was submitted, there was significantly less tunnelling, which is probably best explained in the table on the next slide. So take a look at that. Bored tunnels that have subsequently been added since 2012, so that was during the consultation stage, would be the Norfolk Tunnels East. Somehow the alignment was originally going to be at surface level between Old Oak Common Station and Green Parkway Shaft, alongside the national rail lines in that area. The Bromford Tunnel is a new tunnel, with the original alignment threading its way underneath Spaghetti Junction into Birmingham. Not quite sure how that would have worked. The Chiltern tunnels have been extended by 2.7 kilometres, and there are new cut and cover tunnels at Greatworth and Copthall. So the overall effect, as the table notes, is a 40% increase in bored tunnels and cut and cover tunnels compared to the 2012 route. So that's certainly some food for thought, perhaps, when people talk about cost increases. And finally, before I hand over to Mark to discuss geology, I'd just like to highlight some of the aerodynamic issues that affect the design of the tunnels. I picked this topic as I think it's probably something that not many of us would have paid much attention to before, but it does have a big influence on high-speed rail tunnels. Obviously, it's highly computational, but I'll just sort of talk about three aspects. So oral comfort of passengers is the sensation that you feel when a train enters a tunnel. You can sort of feel a pressure change in your ears. And the requirement is that this must stay below 0.5 kPa over a 1 second period. And this is achieved through a sealed train primarily. But you also have to account for the fact there might be a broken window on the train that might not be completely sealed, in which case you need to be sure you've got an acceptable free area between the outside of the train and the tunnel. So obviously that will have a bearing on tunnel diameter. Second consideration is the pressure loading on the walls of the tunnels and the tunneling equipment on the walls. So as the train enters a tunnel, you get a bow wave of positive pressure that precedes the train, followed by a trail of negative pressure of the same magnitude behind it. So all the tunnel equipment and the structure and certain parts of the ventilation shafts must be designed for this loading, which can be particularly significant for items such as doors. And it's worth noting that these pressure fluctuations will give rise to fatigue loading, and as such, we've done some accelerated testing of our tunnel bracketry, subjecting samples to millions of cycles to try and recreate what it's going to be like over the 120-year life of the structure of the tunnel, with trains every 16 minutes or 6 minutes or whatever it is. And then finally, micropressure waves. So these are sonic booms that, unless mitigated, can be heard at the exit portal as a train enters a tunnel, which can possibly be many kilometres away. So the mitigation is achieved through a porous portal, which is effectively a funnel of increasing diameter, and the funnel has holes down the side of increasing size that then allow the pressure to dissipate as the train enters the tunnel. And you can see under construction on the right-hand side, porous portal at Chipping Warden. You can see the apertures as increasing as the portal gets longer, and then excuse me, in the middle you can see the southern porous portal at the Chiltern tunnels, which gives you a sense of how long these things are. And they're all specially designed for the expected line speed and train and aerodynamic constraints. Okay, let's hand over to Mark.
Thanks, Martyn. Good evening, everybody. In my part of tonight's presentation, I'll be talking about the geological setting of the bored tunnels on phase 1. I'll also talk about some of the challenges that we've faced in tunnelling in some of these ground conditions. Firstly, we'll start off by looking at the geological outcrop map of the Midlands and the southeast of England, which you can see on the drawing. The phase 1 alignment, all 200 plus kilometers of it, crosses several different geological formations, as you can see with the different colors, from the Triassic age in the north to the Tertiary age in the southeast. Starting off with the Bromford and the Long Itchington wood tunnels. These are bored in the Triassic marls and sandstones. Then down in the south, the Chiltern tunnels, and those are specifically in the Mercia mudstone group. Then in the south, the Chiltern tunnels are bored through the Upper Cretaceous chalk group. And then the Northolt tunnels and the Euston tunnels are bored in the tertiary deposits of the London Clay Formation and the Lambeth group. On phase 1, since 2015, HS2 and the contractors have bored over 6,000 boreholes on phase 1 to a drilling depth of over 160 kilometers. So we start off in the north with the Bromford and the Long Itchington wood tunnel. the scope of the BBV JV main works contractor. So as I've just introduced, these tunnels are bored through the Mercia Mudstone Group, and as the name would suggest, these are primarily in mudstones, but it does contain some sandstone, siltstone, and some stiff clays. In stratigraphic terms, they're through the Sidmouth, Tarporley, and the Branscombe formation, but primarily in the Sidmouth. In engineering terms, the mudstone is classified as a weak rock, but does contain some hard beds, such as evaporite minerals, for example, gypsum. And in terms of material properties, it can be quite variable, and this is a function of the state of weathering of the mudstone. So grading schemes are applied to the mudstone to distinguish its engineering properties. In the table in the bottom right-hand corner, it's from the Syria Guide for Engineering the Mercia Mudstone. And this is one of the grading schemes for the mudstone, with grade 1 and 2 being relatively structured rock, so described as a mudstone, while grades 3 and 4 would be more weathered, and in the table described as a matrix, and in the field would be described as a stiff clay. Above the table, you can see a slice through the geological section of the Bromford Tunnel, where you can see the grading on the screen. The grade 4 in the top, grade 3 in the middle, and then the more structured grade 1 and 2 at the bottom. And you can see how the interface is quite varied. In the structured mudstone, the grades 1 and 2 material, discontinuities in the material give it a relatively high bulk permeability. And this has led to some historic challenges in tunneling this ground with high water ingress. Also, the low plasticity means there's a risk of rapid softening upon wetting. And this is a particular problem in tunneling, especially at the cutter head and in the muckaway system or in the slurry system. And this is something that BBV experienced, and I'll be talking about that in a moment. So this is a long section through the Bromford Tunnel, and you can clearly see the variability of the grading, both horizontally and vertically in the profile, the tunnel dipping in and out of different grades all the way along the profile. You can also see the blue line, which is the groundwater, and you can see it's very close to the ground surface. In this slide, you can also see the variability of the mudstone in photographs taken at the TBM cutterhead during a cutterhead intervention. The photograph on the left-hand side is structured ground, so structured mudstone. This would be described as grade 1 or 2. The photographs in the middle and on the right, much more weathered material, and this would be a grade 3 mudstone and would be logged and is logged as a sandy silty clay. So BBV did report some challenges while tunneling in the Mercia Mudstone, the variability of the grading along the alignment, but also the plasticity. They cited the really sticky material in the TBM cutter head, causing blockages in the slurry network, requiring continual adjustment of TBM operating parameters, and requiring regular stopping for cleaning. These were first noticed in the Long Itchington Wood Tunnel, and modifications were made to the flushing system, and there was an improved performance in the Bromford Tunnel. So I'll move on to the central area and the Chiltern tunnels. And this is the scope of the Align JV main works contractor. So these tunnels are bored through the Upper Cretaceous chalk group, and you can see on the long section at the bottom of the page, the grey material is the chalk, with the darker materials being higher weathered chalk and the lighter grey being less weathered. The yellow highlighted zone is the tunnel. And you can also see the green and the orange beds, which are surface deposits of head, terrace gravels and clays with flints. These tunnels bore through almost the entire sequence of the chalk group, from the blocky firm zigzag clay at the bottom, zigzag chalk at the bottom of the stratigraphic column, up to the moderately dense chalk in the top of the strat column. And you can see from the descriptions in the table and on looking at the stratigraphic column, there's quite a lot of variation in the ground that these tunnels would be bored through, from with varying densities of chalk and different layers of marls, hard grounds and flints, and including tabular flints. Also on the section, you can see the blue line, that's the water table. And in this instance, you can see that the depth of the water table is up to 80 meters below ground level in some locations, but in other locations near the River Misbourne, it's pretty much at ground level. So tunneling in chalk can provide some challenges. I've just talked about the variation in the geology. In particular, the presence of flints and hard grounds have the potential to cause high wear on the tunneling machine. But on the other extreme as well, where you've got deep structureless chalk, like we saw under the River Misbourne just now, this can also have challenges because it behaves differently to the rock. It's more like a clay, it's like a putty clay. Similarly to the mudstones, discontinuities in the chalk provide it with a relatively high permeability. And given the depth of the tunnels here, we also have quite high groundwater pressures. In fact, a line reported that they were unable to undertake some of their planned cut-ahead interventions because of the high water ingress. Other structures on the Chilterns that required to deal with the groundwater were the cross passages. And you can see an example in the bottom corner here. This is one of the cross passage locations on inside one of the running tunnels. And you can see it's been peppered with grout ports, trying to seal up the chalk, seal up the discontinuities to allow safe excavation of the cross passage. Also, the shafts on the Chilterns, Martyn's already described, these use long D walls down into the chalk to try and cut off the water to allow them to safely excavate. A further challenge when tunneling in chalk is the soluble nature of the rock. It has the potential to be affected by dissolution. Dissolution causes erosion at depth in the chalk, and over time this leads to opening up of the joints and can lead to openings such as caves underground, pipes as well. Due to the weak chalk, it has the potential to collapse or infill quickly with other materials, and this can include high proportions of flint quite often. The result are solution features left in the ground, which are a risk to tunneling, and this is included in the Chilterns. And this adds just another dimension of variability in the ground that the Chiltern tunnels had to deal with. So the variability in the ground I've just described influenced Align's decision to select a variable density tunnel boring machine. The variable element of the machine is that it can work in variable ground. I've got some pictures here which just were some of the design elements of the TBM, and I'll just talk through those. Firstly, when tunneling in the white chalk, the slurry approach in the machine pumps in slurry through the pipes into the cut-ahead area, and where the mining is breaking down the chalk, the slurry mixes with those particles and holds them in suspension. These are then taken up through the screw and out into the slurry network, where they're taken out to the slurry treatment plant, and the chalk particles are filtered out and removed. The presence of a screw in the variable density machine means it's also able to remove larger sized particles from the cut-ahead, including gravel and gravel and cobble sized materials, which in the case of the Chilterns would be flints. The the drawing at the slice through the drawing in the bottom is from one of the Align TBMs, and you can see the cutter head would be located, sorry, the screw would be located at the bottom of the cutter head. So the more dense gravels and cobbles would fall to the bottom of the cutter head, and they'd be taken up the screw and removed from the cutter head and dropped into this crusher system. The nice colourful image on the right hand side is a bit easier to explain. So those cobble-sized flints or the gravel-sized flints come up the screw, drop into the crusher. So the orange barrel will rotate and crush the particles into smaller particles where they mix with fluid, and then they drop into the slurry system. This allows them to be taken away in the slurry network without causing damage to other equipment on the slurry system, like the pumps. Align reported that the variable density machine performed well in the Chiltern ground conditions. In particular, the screw and the crusher mechanism were invaluable in dealing with the hard flints, which at times took up about 10% or sometimes above 10% of the face, the excavation face. So I'll come on to the south area and the Northolt tunnels and the Euston tunnels, which are the scope of the SES JV Mainworks contractor. So the geology of these tunnels is the London Clay Formation, the Lambeth Group, and with a small section dipping into the top of the chalk. On the long section at the bottom, which is from West London, West Ruislip in West London, through to central London, this is Euston Station. You can see the Northolt tunnels and the Euston tunnels on the profile. Northolt tunnels split between east and west. You can also see on the long section the structure of the geology in the area, with the green chalk dipping down into the London basin structure with a deep infill of London clay over Lambeth Group. The orange is the Lambeth Group. So starting from the west, the Northolt tunnels dive down through the London clay and into the Lambeth Group and chalk, where they tunnel along that interface for about 2.3 kilometres. Then the tunnels entirely in Lambeth Group for a further 6.5 kilometres until about 2/3 of the way along the Northolt tunnels. The eastern part of Northolt tunnels and the Euston tunnels are all in the London clay. The table above shows the geology in a little bit more detail. And you'll note, in comparison to the well-known geology in central London, the lack of thanate sand between the chalk and the Lambeth Group. You can see the blue layer here is thanate sand in central London, and it peters out just to the west of Old Oak Common. You'll also note that the Lambeth Group consists of the Up North Formation. There's a small amount of Up North Formation, and it's overlain by the Reading Formation. There's no Woolwich Formation in the area. And the Reading Formation is made up of the Upper Mottle Clay and the Lower Mottle Clay. And finally, of note, the presence of sand channels in the Mottle Clays. I'm going to talk about the Lambeth Group in a little bit more detail in the next slide. So in this slide, we're showing the more detail about Northolt Tunnels West. This is because of the variable geology in the area, in particular the notoriously variable Lambeth Group. On the section here, this is the first 4 kilometres of Northolt Tunnels West, so kind of zoom in on the left-hand side of the previous slide. The tunnels dive down into the Mottle Clay, which is the beige material here. And you can see it encounters these yellow channels along this first 1 or 2 kilometres. And these are the sand channels. And you can see they're encountering them at the face of the machine and also above the crown of the machine. And this did cause us some challenges whilst tunnelling the Northolt tunnels. And I'll talk about that in a slide later on. The channels are a common occurrence in the Mottle clays. They were deposited as sand, silts and clays in rivers that were formed during that time. In HS2's formation expert Jackie Skipper's work for SES and HS2 in the area, she posed that these channels were likely deposited in a floodplain environment, as meandering, cross-cutting and overlapping channels. And this is similar to that mapped by Harold Fisk in the Mississippi floodplain. That mapping is presented in the bottom right-hand corner. And you can just see how the channels develop with time, and the meanders change and they start to cross-cut and overlap each other, and how this would translate to being quite variable ground and challenging to tunneling in the future. The high variability can also be seen in the figure here, which shows the design profiles, geological profiles for the first 10 cross passages on Northolt Tunnels West. These cross passages are 4 meters in diameter, 11 meters in length, and they're built with the spray concrete lining method of construction. So the challenges we would see here, of course, would be the green chalk, the water pressures in the chalk, either below the invert or in the invert or just below the invert. And then the yellow sand channels being in the face of the cross passage or above the crown of the cross passage, with a risk of water inundation or potentially face collapse. These issues were identified during the design phase, and when considering the safest approach to building these cross passages, we're looking at grouting, dewatering, depressurization, and freezing. SES selected the freeze approach, artificial ground freezing approach, for the most onerous conditions. The freezing approach was scored highly for both safety and program criticality. HS2 also recognised the risk of these particular tunnels and requested that the independent tunnelling expert panel undertook a review of the SES proposal, which they did, and they fully endorsed the solution. In the end, of the 21 cross passages that were in the Lambeth group, that included 1 cross passage on Northolt Tunnels East, 12 were frozen, 5 were dewatered, and 4 didn't require any treatment. So in this slide, you can just see one of the cross passages that's been frozen, from the design through to the mitigation and the excavation. So in the left-hand figure, you can see the geological profile of cross passage 33 next to the running tunnel and the cross passage off to the side. You can see the same risks we talked about earlier with the chalk in the invert, so the water-bearing permeable chalk in the invert, and the sand in the face or near the crown of the tunnel, both with the potential for water ingress or potentially sand coming in. The ground freezing mitigation option mitigates the problems associated with that ground. In the photograph in the middle, you can see the installation of the artificial ground freezing mitigation. The freeze pipes have been drilled around the perimeter of one of the cross passages this is the running tunnel, and it's all been connected up to the pipework for the brine system, and this circulates and freezes the ground. So the white on these pipes here is ice that's built up on those particular connections. The black material is an insulation on the inside of the running tunnel. In the graph in the top right-hand corner, which is a little bit vague, sorry, you've got time against temperature, and this just shows the freeze-up process. So started at 17 degrees and dropped to between -5 and -20 degrees over a 2-month period, at which point it was ready to be excavated. And then in the photograph on the right-hand side, you can see one of the excavation faces, frozen clay over the frozen chalk with flints, and you can see it's all standing up nice and vertically. There's no water ingress, good conditions for mining, nice and safe. And this slide, we've got another cross-passage face, this one with the sand channel sitting over the clay. And considering what we were talking about with the potential for the water-bearing sand to collapse into the face, you can see how well the artificial ground freezing has worked. It's standing vertically over the clay. nice and safe. Again, good conditions for mining. So we also faced some challenges whilst tunneling in the Lambeth Group sand channels with the TBM. As we saw in an earlier slide, the sand was encountered in the face of the machine and also above the crown. And this, because of the non-cohesive nature of that channel material, has the potential to unravel above the machine. And this did occur in some locations on the Norfolk Tunnels West, especially in the first 1 or 2 kilometres. The contractor SES managed this with their standard TBM operating procedures. First of all, using the Norfolk Tunnels West machine was bored in full earth pressure balance mode, so there was always pressure on the ground. And also using the tail skin grouting to fill the annulus around the lining. You can see those in this top picture, just about. The grouting would be done behind the shield in the annulus around the lining, and then pressures held on the face. In the shift review group, tunnel boring machine parameters, instrumentation and monitoring data, asset protection data is all reviewed together and considered. This included the spoil grout reconciliation, and this was the first, this is where unraveling sands were first identified. The spoil grout reconciliation process is where the spoil that's actually been excavated from the face of the TBM is the weight of that taken from the belt weighers on the TBM is compared to the theoretical weight of the soil from a ring plus the volume of grout that's been put in around that ring. And where the data suggests there's either a gap in the grouting around the lining, or in this case, an unraveling sand, the SRG is able to instruct the tunneling team to undertake probing and potentially secondary grouting from one of the backup gantries if it's required. In these particular conditions, SES used some additional measures. They had some conditioners which were designed specifically for working in granular ground available to them as and when they needed it. They put bentonite under pressure around the shield, and you can see that in this figure in the top right hand corner. So the bentonite is injected up under pressure around the shield to support the ground above, and in the case here supporting the yellow material, which would be the sand channel material, and hopefully stop it unraveling. They also used an increased frequency of probing and longer, deeper probes in this particular ground. So the reconciliation process continues until the SRG are completely satisfied that the rings are completely grouted in place, and the same information goes to an independent party for a Category 3 check. The process is supported by is complemented by the instrumentation and monitoring, which is maintained on the surface for at least 4 months after the TBMs have gone past the area. And this goes through a very robust closeout process requiring ratification at the Contract Technical Committee, the CTC, which has the oversight of the SRGs and the tunnelling. The ground movement in above these tunnels was minimal, even given the potential for settlement where unraveling sands had occurred. The volume losses were maintained to about 0.4% or lower, which was an excellent result. So SES have successfully navigated the tunnelling through these ground conditions, and these tunnels are now complete. And you can see a photograph in the bottom right-hand corner of one of the machines being removed from the ground. Thank you very much. I'll hand back to Martyn, who's going to talk about data.
Okay, thank you, Mark. So we launched our first TBM in May 2021, and we've been gathering data ever since. And this slide shows some of the tunnelling milestones that we passed compared to other tunnelling projects in London. You can see that after 2 years, we surpassed the length of tunnel from the Jubilee Line extension. Not long after that, we passed Tideway and London Power Tunnels 1, London Power Tunnels 2, and 3 years after the Chiltern tunnels were launched, we'd driven more tunnels than Crossrail. So we've now driven nearly 75 kilometres of TBM tunnel, plus about another 2 kilometres of SCL line tunnel if you add in all the adits, cross passages and the old common tunnels. And that's about 80% of all the phase 1 tunnelling. And we've been tracking this, as I say, we've been tracking this data ever since through the SRG minutes, etc., etc. And we developed our own Power BI dashboard. So this tracker is kept up to date, and it shows on the right-hand side, possibly not the best view, but that's the geological review of what progress is. In the middle, we've got daily, weekly, monthly rates and so on, and cumulative on the left-hand side. And you can adjust this for any particular time period to see how we're doing at any one point in time. Now, obviously, there's quite a lot to see on this slide, so I've extracted out information that you're probably all interested in on the next slide. So this shows advance rates for all of our different TBM tunnels. TBM drive on the left-hand side, and then daily, weekly, and monthly advance rates in the columns to the right. Obviously, you can't compare different drives, different ground conditions, all sorts of issues, and unforeseen events can conspire against you to affect the overall rate. So don't take it too comparatively, I don't think. But a couple of things to note, that by and large, each drive wasn't that far away from achieving the programme progress rates they set out to achieve. So the programme rates are in the second column, the daily programme rates, and then the average is in the column after that. So they don't particularly far away. And although we almost, but never quite managed to get to 1 kilometre of tunnelling in a week across all of the drives when we were fully motoring, I think, all of the weekly and monthly rates are pretty impressive. And for anyone interested, these are rolling averages. Okay, so this slide shows TBM utilisation, again by TBM, with the blue being utilisation and the orange being standstill time. Just to say, I have run this past all of the contractors now, I'm happy for it to be put up here. You can see there's a wide range of outcomes. Again, there's many reasons why one drive may be better than another, better, so to speak, quote unquote. It's worth noting that the Atlas Road logistics tunnel on the right-hand side has been stood for longer than it was bored, but that's skewed because it was a very short tunnel and it was stood for a couple of months without doing any mining. The other data we've been gathering is volume loss. This graph here shows the volume loss by chainage and ground conditions. So we've got chainage along the bottom, volume loss up the side in percent. The blue circles on the left-hand side are the London clay on the North Tunnels East Drive, followed by the solid grey dots of the North Tunnels West Lambeth group, and the orange dots of the chalk of the Tilton tunnels, and then the blue triangles and black dots are the mudstone of the Long Itchington Wood and Bromford tunnels. So generally speaking, as Mark has mentioned as well, we are well below the contract value of 1%, with the highest values being for North Tunnels East, which was driven in a semi-open mode, so it's not really that surprising. The volume loss values for Tilton and Bromford tunnels quite often in the chalk and the mudstones were so small we couldn't even measure them, except for a small spike towards the end of the north end of the Chilterns. And this slide shows some of the ways that this information has been depicted for us. On the left-hand side, the image shows the Align volume, one of the typical Align volume loss curve, and you can see the green line is pretty closely following the prediction, reasonable correlation. The middle one is for the Bromford tunnel, where almost no settlement was measured at all. That is for when the tunnel went through. That's not just instrument noise or anything. That is the settlement we got. And then on the right-hand side, the table show from SCS shows some of the very low volume loss figures that they've been producing as well. Just sort of a final word on this, I think. We notice on some of the contracts that we seem to have consistently installed arrays that are too short to reach across the settlement trough. So either we've got the trough width coefficient wrong, or for one reason or another, we haven't been able to install the arrays all the way across. So probably in terms of monitoring for instrumentation for set protection and stuff, it's been fine, but for back analysis, it does make it a little bit more difficult. So perhaps something to think about going forward. And then, so what are we going to do with all this data? Well, it's already been mentioned earlier on today that we're currently working with City St George's University here in London to provide them with the construction monitoring data and associated TBM location data. And they're going to put that into a legacy archive for any interested party to get access to and do research and what have you on. So there'll be more on that when we have it, hopefully in a few months' time. So the future, what's still to be done? I mentioned that we've done 80% of our tunnelling, so that still leaves 20% to go. So what does that consist of? The Euston tunnels are going to be launched in Q1 next year, and they're going to be launched from the stub tunnels at Old Oak Common Station that I described earlier. So these are 7.55 metre diameter, 7.3 kilometres long, and then 19 cross passages. So as mentioned previously, both EPBM machines are now pretty much fully assembled in the stub tunnels and ready to go. It's been a real life game of Tetris for the SCS team, with access through the station box having to be coordinated with the station box contractor, TBM and gantry delivery and availability. The roof is now completed over the top of the TBM assembly area, and the only way in or out now is the Atlas Road Logistics Tunnel. And as you can see in the image on the right hand side, this is still relatively clear, but soon enough that'll be full of a conveyor belt, leaving quite a small opening for access. The TBM, these TBM drives don't end in a traditional reception chamber. We've had our last proper breakthrough in that sense on Monday. They're going to finish in SCL chambers where the machines will then be broken apart and disposed of back up through the Atlas Road Tunnel. So what will that look like? To answer that, I first need to describe a little bit the complexity of the Euston connection. Okay, so in order to achieve the number of trains per hour, and therefore the number of platforms that's required by our sponsor, we need to have 2 uplines coming into the station throat. Otherwise, there'll be too many conflicting moves where a train coming into the platform is crossing in front of a train coming out. And that leads to instability in the timetable. And as soon as you have slight perturbation, then it all falls over and you can't run your service. So I've attempted to describe this in the flat junction and grade separated junction stick diagrams on the slide here. So basically you have, on the left-hand side, you have the flat junction. So you have a single upline coming in and a single downline going out of the station. So if you look at the upline, all the trains coming in, if the trains are coming into the station, into the western platforms, those 3 rectangular boxes at the bottom, they will be crossing all the trains coming out of the eastern platforms onto the downline coming across. So those ones coming down there will be crossing those ones coming out there. So in order to alleviate that, we have 2 uplines instead. And that's what the grade separated junction shows on the right hand side. So you have your upline splits into 2, and one of those uplines goes either under or over the downline and services each sort of section of the station, if you like. And that way you reduce your conflicting paths and you don't have as you don't put your timetable as much risk, and you can have a better service. So due to the constraints vertically and the vertical alignment in the Euston area, this bifurcation or flow under has to take place underground, hence the Euston caverns. So these images from the SCS bin model show what the intention is. So we have the 2 TBM drives finished in a short reception chamber for the downline, which is just there. So that's the TBM tunnel coming in, that's the reception chamber there. And then the upline finishes in a larger cavern, which is here. So the cavern allows the upline to be split into 2, as required to service the station platforms, through a binocular tunnel, and it splits into the upline east and the upline west. And the upline west drops underneath the downline, which then rises above it, and then all 3 snake their way into the Euston scissor box at the end of the station throat. So the cavern is quite large, and it's actually 3 caverns in increasing size, 11 metres, 13 metres, and 15 metres across the axis. And the cavern itself will be driven from a crosscut adit, which in itself is a massive excavation, which is driven out of the bottom of the Euston shaft, which you can see in purple on the diagram. So in order to minimise ground movement in the larger size cavern, the way we've elected to do it, or the way SCS have designed it, is to have the outer line of the cavern driven as a series of interconnecting stacked drifts. So these are SCL tunnels about 2.5 metres in diameter, driven from the crosscut adit, which is subsequently then backfilled with concrete to form like a pipe arch over the cavern. And then the cavern itself is then excavated in the traditional heading bench and invert methodology. So it's quite complicated. I probably haven't described it in nearly enough detail for you to understand it, but just to give you a flavour, it's going to be a critical piece of construction, not least of all because there's, I think there's 10 lines of the West Coast Main Line relatively close above, and a delicate network retaining wall to the side. So I'm sure when that all starts in a couple of years' time, we'll be hearing a lot more about it. So that brings us to Euston. Hopefully that's given you a flavour of what we've achieved and what's still to come. I'm just going to finish off by playing a short video of the current route-wide HS2 progress. Hey, thank you. Take any questions?
Thank you very much, Martyn and Mark. Certainly given me a much better appreciation of the vastness of the project and the complexities. So yeah, can we take some questions, please? And if you can knock the spotlights down a little bit, Gabbo, please. Thank you. Okay, any questions? Must be.
Good evening. Thank you so much for that presentation. That was fantastic. My name's Naomi Barrington, and I'm a civil engineer, project knowledge manager at SES. And I had a question regarding innovation. Could you share a few elements of innovation that you might have implemented across HS2 in regards to tunneling or boreholes, or just something along that would be great. Thank you.
Okay, I'll try and remember some. But I mean, obviously we have a whole innovation platform that's just looking at stuff all the time. We did a lot of research earlier on into carbon-free or reduced carbon SCL linings, that got so far and then didn't progress any further, unfortunately. We certainly installed low carbon concrete on, and certainly as temporary works in some of our sites. I guess we've gone diesel free on a couple of our construction sites. In terms of tunnelling, I mentioned that EKFB were doing quite a lot of innovative stuff at trying to improve the productivity of the green tunnel installation. I'm not sure how much that is innovation or just kind of process improvement. There is there is more. I'm sure I can't think of any off the top of my head.
Okay, next question, please.
Good evening. Thank you very much for the presentation. It was brilliant. And just following on to that innovation question, as most innovation comes with a certain risk, I was wondering, how do you manage the uncertainty that comes with an innovation that you've implemented on HS2?
Okay, yeah, that's a good question. And I think clients are sometimes seen as a little bit risk averse when it comes to new products and new ways of doing things. Well, and we have a pool of subject matter experts who, in all fields of civil engineering, materials, etc., and we do look at stuff. We do have, and we have our standards and our standard specifications that people need to adhere to. But if someone has an idea that they think can save money that departs from that, and they can present that to us, then we're more than happy to consider stuff and implement things that might be slightly out of the norm, I'd like to think.
Peter Townsend, I work for Mott MacDonald. The GBR and claims from the contractor, how is the GBR on various packages formed? Has it proven well?
Yeah, you can do that. You can do something.
Well, the GBR is the contract document. In the case of the HS2 contractors, they were prepared during the IPT phase, so they were prepared jointly between HS2 and the contractors. I can't really say how they're performing at the moment. They're written, they're in use, the contracts are live. We are dealing with compensation events as we speak against the GBRs. The GBRs are black and white. It's a baseline, so it is what it is. What do you mean by performance specifically?
Well, have you found unexpected ground conditions not found in the GBR and in regards to your compensation events? Are they relatively low that the contractors been putting in?
Yeah, I think it's fair to say we've had a few, ground conditions compensation events, and we've used the GBR to look at those. Obviously, there's two sides to everything. We have a view, and the contractor has a view. Have we found any where the GBR has been silent? Yeah, I think so. There's probably been a couple of occasions where we've gone to look in the GBR for guidance, and it hasn't had any, which is, I guess that's your question, how are they performing well in that instance? Perhaps not as well as we might have hoped, but generally speaking, we've been able to use them for what they're there for.
But the point is that a GBR has got baselines in it. If the baselines don't cover something, then you use the contract mechanism for physical conditions. So, which would be going back to the site information, the pre-construction information, for example, or the ground investigation as well.
Okay, take one online. James, have you got one, please?
Yes, we've got a couple of questions online. We've got one from Philippa Halton, and she was interested in the Mercia Mudstone tunnel profiles. And the question is, why do you think the weathering grade profile was so highly variable? And just for my own interest, if you'd like to comment on the Mercia Mudstone, but was there anything in the weathering profiles of the chalk as well that was interesting?
I think this is probably a question better answered by the contractors, to be honest. I mean, the profile I showed was probably based on the original ground investigation. So obviously the spacing of the boreholes would have influenced the erratic up and down of the weathering profile. Not sure about the mudstone, but
We did find, certainly there was a lot more water in places than we expected. There was a lot more fractured. I think that was more towards the centre of the Bromford Tunnel. And that did have an effect on TBM progress. We had to do some remedial work to the machine and change how we did things. So it was definitely, I think it was more variable than expected. Whether it was more variable than it would have been expected had we done different GI, I don't know.
and with the chalk, obviously where the River Misden was, there's quite a deep weathering profile. But a line didn't have any problems tunneling in particular in those conditions.
All right, question from the audience. Yeah, down here, we'll take you next. Charles first, yeah.
This is on, yeah. Yeah, Charles Allen, independent consultant. Could the panel just give us an update on the status of the cost and programme of the HS2 civil engineering works, please?
No, because I don't actually know. We are, as you probably know, we're going through a period of a reset on cost and programme. I couldn't tell you where that's headed or what it's saying. I'm sure it's going upwards and outwards, but that's not really for us to give an opinion on.
I speak as a taxpayer.
Okay, thank you, Charles. Who had it?
Phil Quelch Jacobs. Old question, but it's favourite. If you're doing it again with what you know now, what would you do differently as a client?
What would you do differently? Do you know?
Well, but yeah, I mean, potentially the ground investigation you might do, the way the ground investigation was set out was to do a sort of an initial investigation with the spacing sort of compliant with the EC7 spacings, and allow, because the contractors came on board early, so the idea was that they would be able to fill in the gaps or focus investigation where they felt it was most necessary, which I think probably did work. But at the other side of it is that is there enough information in the first place to price it properly? I think we could say that. So maybe the investigation you might spend more, but when you think about the size of phase ones, the amount of money was spent on ground investigation, you've got to convince somebody in the government or the DFT to give you more money to do more investigation, and it's quite difficult sometimes.
Okay, one up in the corner, there was a, yep.
Waka Samad, I used to work for Yale Tech. One of the problems that we've come across is London clay. It's a very bad reputation because it's been used in embankments. How have you managed, given the fact you must have known about London clay's reputation, its poor moisture capability, the fact that it's known or blamed for subsidence, have you managed that for HS2?
Well, I don't think there are any London clay embankments on High Speed 2, for a start.
What will we reused it as?
Oh. I'm not sure where it's going. Where's it going? Soil treatment plants in... actually, I don't know the answer to that. All of the material in West Dry Slip has gone to a sustainable placement area, which is in land to the west of West Dry Slip, and it's all placed and filled. I don't know where the Euston Tunnel stuff's going, actually.
I'm not sure.
Sorry, I don't know the answer. If anybody else wants to join in, and please feel free. No. Sorry.
Okay, Rosa?
Yeah. Rosa T. Edmond McDonald, considering this was the first time that the variable density machines were used in the UK, basically that extensively, in hindsight, do you think that, so first of all, how did you think they perform, and whether they were the right choice for the ground conditions in the north and the Chilterns?
Okay, so I think certainly there's evidence that the Chiltern tunnels that was put to good use, particularly the first section through the M25. They wanted some reassurance that we weren't going to get any movements there. And I understand that the density was certainly pushed up as you went underneath the M25. And I understand that again, as going through expected dissolution features, the parameters were adjusted using the facilities on the variable density machine to good effect on the first drive, and the second drive came along and learnt from what the first drive had experienced in terms of that and did the same. So I'd say certainly the Chiltern tunnels, yes. The Bromford tunnels, I must confess, I'm not entirely sure. The conditions were perhaps less variable there, requiring the variable density machine. And perhaps it was more of a belt and braces option in the first place. But I think you'd probably be best asking the contractor if they felt that it was worth the additional effort.
Yep.
Hi there, thanks for a good presentation. What percentage of the journey is actually to Birmingham in tunnels?
About
Time
20%.
Do you know what that is in time?
Sorry, in time?
Yeah.
20% of 45 minutes. So
Oh, okay.
I guess it's approximately, obviously, and some of the tunnels are full speed. Some of the tunnels, certainly closer to London, it's only 120 kilometers per hour rather than the 360. So, you're looking at about 12 minutes, I guess.
Okay, thanks.
Yep, one up the back there.
Just to ask, what
Can
would
you
the
give your name as well, please?
Sorry, my name's Isuri, and I've worked for the Euston section before, but as a client, what is your considerations for changes? Because I've seen so many changes along the line for design. What are your considerations? I know that the contractors do give you a little bit of support with what they know, but what are the considerations that you as a client take when you change the design or when you accept these conditions?
Okay, so from my perspective, I've only been on the project for 4 years, so we've been resisting change now because any small change leads to a huge cost change. So, we have our standards and our requirements, and we have a very strict rule at the moment that there'll be no changes to those unless it's a safety critical, basically, because then because otherwise it turns the contractor away from delivering and moves the focus, and the cost just is too much to bear. If you're talking about sort of wholesale major design change, then again we have depending on which contract, you have a different process to kind of accept that change, although it's generally the same, but depending on the magnitude of the change depends on how stringent the process is, but it's got to be demonstrably good value, or we won't be accepting it.
Okay, maybe one more question. We got one. Okay, well, thank you very much for excellent presentation. Just a couple of announcements before we finish off. So tonight, can you move the slides on, please, Gabor? Yeah, excellent. So lower ground 4, food and drinks, sponsored by EDP. Moving forward together. Thank you very much. Okay, so Divik's going to say a few words now about Dave Carver.
So we're quite sad to announce the passing of a friend and much loved colleague to many of us, including a lot of the BTS members. Dave Carver will always be remembered as a delightful individual and a very competent tunneler and an avid biker. He leaves behind a legacy of his immense contribution to projects such as Hindhead Tunnel, London Power Tunnels, Tide Bay, and most recently Hinkley Point C. The BTS would like to extend their condolences to his friends, his wife Ginny, and his 2 children. Back to you.
All right, thanks, David. Where was he working? Say
He was Hinkley's final project was
final
Hinkley Point
project.
C.
Okay, and you say he was working up till September. Did you August or September?
August, I believe. If I can be corrected, I believe it's August. Jim.
Wow.
And then we were at Hinkley as well. He took good care of us. He used to invite us around for, live locally, so he used to invite us around for lunch over the weekend. So, very good guy.
Okay, thank you for that.
Great loss.
Okay. So the young members annual conference is next week, I believe. 24th of October, which is at the Arabs office. And if you want to go, you can get tickets. There's a QR code there, or you can go onto the British Tunnelling Society website. I went last year. It's a packed agenda, lots of great speakers, lots of energy and enthusiasm. So, Scott, what? Sorry. Oh, okay. Next slide. Yeah, right. I see. There you go. Okay.
I haven't talked of BTS member yet, but one should become a member in the next few months. And you can come and see me or a few members of the BTS coming here as well. No, we talked to somebody from the BTS and we still get you in for free next week as long as you follow up with the membership.
There you go. Thank you. On the 6th of November, the BTSYM AGM and their November meeting is on Connecting Worlds Underground, Digitalisation in Tunnelling. So that's Thursday, the 6th of November. And our next evening meeting is on the 20th of November, and it's on carbon management for the metro projects, the Copenhagen Metro. So that's Thursday, the 20th of November. And then finishing off the year on Thursday, the 11th of December, it is Professor Colin Eddy and Dr. Henry Parado, and they are talking about slipform tunnelling, revolutionising tunnel construction. That should be well worth attending. The British Tunnelling Society Health and Safety course is in November. It's on Monday the 17th and Tuesday the 18th of November. We've already taken a lot of bookings, so I'd encourage you, if you've got people you want to send or you want to go on it yourself, to get onto the website and book. It's very good value for money. This year we're having it at Arabs office rather than here. We usually have it at the institution, but we've moved to Arabs this year. So yeah, 17th and 18th of November, and there's a whole range of speakers there. All right. And our biannual conference, I should say. We've set the date now, which is on 6th and 7th of October, 2026, and that's in the Queen Elizabeth Centre, just around the corner there. So put that in your diaries, please. And there's a couple of announcements now from the British Geological Association.
Thank you. Yes, just a few slides with our events. We've got the upcoming 2025 Fleming Awards. The deadline for applications, you're going to have to be quick, is tomorrow evening. But hopefully you've already submitted. There will be a £1,000 prize donated by Cementation Skanska, but the finals, which you do have time to register for and come to, will be on the Tuesday, the 2nd of December 2025, and as usual, they will be here. There is also, whilst to give the judging panel time to judge, there will be a presentation as well. The British Geotechnical Association Early Careers Group will have its annual networking and welcoming event for 2025. This is a fantastic event. Last year, I believe there were over 100 people, and this will be on Tuesday, the 23rd of October, 2025. Advanced registration is required. And we have the Geotechnic lecture, which is clay behaviour through the keyhole by Professor Beatrice Baudet from UCL, and that is on Tuesday, the 4th of November, 2025.
Okay, so final slide now, just advertising our book. We've sold well over 1,000 copies, but we still have a few left if anyone wants any. £65. And if you're not a British Tunnelling Society member, just encourage you, if you would, the more people we get in the society, the more we can get actively involved in our industry and what's going on, and people can give a bit back as well. So there's a QR code there. It's very good value. I think it's £93 for a year. So yeah, if you're not a member, please consider it. And that concludes this evening. Thank you all for turning up. It's brilliant to see so many people and to fill this theatre.